Hi, this is our team Bolt. This is our video presentation for the spring 2021 semester for Mechanical Engineering Department. Our teammates this semester were Austin Barnes, Callie Edwards, Chase Fell, Aubrey Lejeune, and Bhavani Simon. This covers our 2021 project schedule and responsibilities. This is a task we sat down in the fall semester to discuss which projects were going to be individual and which projects were going to be group assignments. So this was a really important task for us to make sure that we hit all of our deadlines through each semesters and that we finished our project on time. This is our budget and funding for our 2020-2021. This is our cost analysis. So budgeting can be really hard for projects like this. You have to be sure to take into account for all of the factors, including the unknown factors that can come up throughout your project. So we were able to stay on task for ours and keep it under budget from what we raised from our funds. This is our concept generation for 2020. We used a decision matrix to determine our priorities for our bike. So you can see we used the frame, rear basket, solar panel, and wiring, the change drivetrain, the shield, and the tune-up for our factors. And then the qualifications, you can see we had a few as speed, agility, weight, durability, complexity. And you can see from the total at the bottom with the numbers, basically our main priorities that we decided to work on for both semesters. Along with our concept generation, our team worked together on the material selection for our shell. Material is an extremely important factor in the success of any project. There were a lot of characteristics you have to consider, but our main priorities were durability, cost, visibility, ease of construction and mounting, availability, and weight. Although all of these are factored in, durability, cost, and weight were our main priorities. And while plexiglass looks like the best option, after further research, we decided to go with Lexan, which is a polycarbonate material instead of an acrylic material. It was our best option cost-wise, and it also gave us great visibility and durability. Safety is the main priority in any project that you work on. For our bike, we had specific safety requirements for the competition, and a few of them were we had to come to a complete stop from a speed of 25 kilometers per hour and a distance of 6 meters, which is 19.7 feet. We had to turn within an 8-meter radius, which is 26.2 feet, and then traveling for 30 meters in a straight line at a speed of 5 to 8 kilometers per hour, exhibiting stability. So also along with the safety requirements for our vehicle, we were required to ensure during a collision or tip-over event that our drivers remained in the vehicle without any body parts touching the ground. So you can see demonstrated in these pictures, our safety harness did a really good job of keeping us safe and in our bicycle. Analysis is a really helpful tool, and this was required for our rollover system. To calculate the deflections on the roll bar, the team used SolidWorks modeling in order for the computer to calculate the deflection. The program requires the variables mentioned above, and the correct type of steel tubing needs to be inputted into SolidWorks in order to accumulate the correct information that the computer calculates. Provided are the models of the roll bar using a top load of 2,670 newtons, 12 degrees from the vertical, and a side load of 1,330 newtons at shoulder height. The top loading yielded a deflection of 1.26 centimeters, and the side loaded yielded a deflection of 0.98 centimeters, which means we successfully meet the ASME standards for this competition. Another analysis performed was on the steering system. We used the Ackerman steering calculations, which used physical dimensions such as frame length, wheelbase width, and turn angle to find the turning radius, which is within competition specifications. The tip-over calculations were based on the sum of moment at the front tire when the centrifugal forces are exerted from the center of gravity. MATLAB calculations were used for the formulas of the sum of moments, force values, and the center of gravity to analytically find the max speed before tip-over. For safety purposes, a speedometer should be used for the driver to judge turns. The next analysis performed was over the gearing system. To start the analysis, our drivers were put through various physical tests to determine high-end and low-end rider cadence. 100 RPM was chosen as the high-end cadence, and 70 RPM was chosen for the low-end cadence. The gearing for the analysis is a 3-sprocket chain ring with a 9-speed rear wheel. The table shows selected gearing ratios and cadences with resulting speed outputs. Our max speed under peak driving conditions is a suitable 27.97 miles per hour. This max speed fared well in our competition, leaving us plenty of low-end gearing for fast acceleration and low-end speed driving. Once we decided on a material for the shell, we built a model and ran simulations in SolidWorks. Our focus was where to attach the shell to lessen vibration. As you can see from these photos, when only attached to the top and the bottom with a 15-mile-per-hour headwind, there's a great deal of vibration. This will lower our aerodynamics, distort visibility, and potentially put the driver in danger if the material were to shatter. So we chose to attach the shell on all 4 sides to increase our aerodynamics and the overall safety of our bike. These are updated detailed drawings of our official design of our aerodynamic shell. And here is where we completed our HPV model in SolidWorks with the complete model of our shell and frame for our bike. These pictures show the steps that were taken to do our mold design that will be later discussed. As you can see in this picture, this is our first failed attempt of our shell. A few things that went wrong with this is we misjudged heating an entire sheet of polycarbonate all at one time. We miscalculated the heat loss during the transfer to form. This heated in a heat sink for 5 hours. And then we also had problematic transfer of shell to the mold. Here you can see our final product, and these are the steps of the molding assembly process. First, we used original drawing to create 3D pieces from SolidWorks. We transcribed these to G-code to input in the CNC machine. Then we covered our mold with strips of tar paper to form solid mold. We covered with the aluminum foil and adhesive to heat the shield. We then placed the mold in the oven, which was required to be heat soaked for several hours. The optimum temp is between 210 and 220 Fahrenheit until this mold was soft and formable. So once the mold was done, we allowed to cool for several hours. We then welded 1/2-inch blocks of glass to the nose and rear rim, and this just increases the thickness to support the bolts and brackets. After that, we drilled and bolted the hinges on the rear and a latch on the nose, and then assembled our roll bar to the nose of the bike frame. For our last slide, we have a suggestion for the next team's innovation design idea. In a previous competition, this bike tipped over at every turn. We made several structural changes and completed multiple types of analysis to find the safe range of speed at full turning radius. Our suggestion for this would be a dynamo charger to power a cell phone and allow GPS application for the rider to be fully aware of the speed they are achieving in order to avoid a tip over scenario. Thank you for your time. We hope you enjoyed.